All right, let's go through challenge day number 2 together here. So number 1, in the diagram, the measure of angle 4 is equal to the measure of angle 5. So maybe I go ahead and just mark those two angles congruent to each other. So there's angle 4, there's angle 5, okay? And segment SE, so here's segment SE, bisects, ooh, we got some old chapter 1 stuff going on here, angle RSF. All right, so if an angle is being bisected, that means it is being cut into two smaller equal-sized angles. So that would be angles 2 and 3. Now, here's the thing. Initially, I don't know that angles 4 and 5, which are congruent, are the same angles as angles 2 and 3. So for right now, I'm going to go mark angles 2 and 3 with 2 congruent markings. Now, I want to explain that currently I don't know if all 4 of those angles are the same, or if 4 and 5 are the same and 2 and 3 are the same, but they're not all the same as each other. All right? So I just want to throw that out there. 2 and 3 might be the same as 4 and 5, but I currently don't have enough information to conclude that. So in the end, we need to figure out what is the actual measure of angle 1. So angle 1 over here. Now, initially you might be wondering, how are we going to figure out how big actually angle 1 is when we were given literally 0 values in this entire problem, right? We don't even have a 90-degree angle, let alone anything else. So how are we going to figure out angle 1 when we don't have any actual values? Now, some things to point out. We know that angles 1, 2, and 3 all added together because they use the same vertex point here. They have to add up to be 180 degrees by the straight angle postulate. But we don't know how big angle 2 or 3 is. We just know that they're the same value as each other. So here's where we're going to start doing some exploring. All right. So, and I said no formal proof is required here. So we're not going to necessarily write like a statement and a reason and a statement and a reason, but I will kind of present it that way just a little bit. All right. So we know that angle 4 and angle 5 are equal, and that was just given to us. And we know angles 2 and 3 are equal to each other really by the definition of bisect. We were told that an angle got bisected, so we need to define what that means mathematically. And we got that that meant angle 2 and 3 were the same. Okay? Now, there's other angles in here that we really need to discuss. And if you didn't notice, there are some parallel pieces going on here. So these two segments, FS and ER, are marked as parallel. And so, hey, we've done this whole chapter on parallel lines and segments, and we've even done a ray problem. Do you see any kind of special angles that we could maybe discuss here? And I just want to point out a couple in general here. And the first off being, if I can get a different color here, angle 4 and angle 2. Notice angles 4 and 2 are alternate interior angles. And in the presence of parallel lines, angle 2 and angle 4 are really equal to each other, right? So by the alternate interior angles theorem, we know that they're equal. Now, what about angle 5 and angle 1? Because I want to talk about angle 1 at some point in this problem, right? And notice angles 1 and 5 are corresponding angles. So angle 1 is going to be equal to angle 5 by the corresponding angles postulate or theorem. I'm not going to be picky about that. And so notice now, look at all these wonderful angles we've got. We know that 1 and 5 are the same. We know 2 and 4 are the same. We know 2 and 3 are the same. We know 4 and 5 are the same. Is it going to end up being true that all 5 of these angles are really the same value as each other? I mean, could we actually draw together all of those pieces and conclude that they all must be the same by using, I don't know, substitution or the transitive property that we've been using a lot so far this chapter? I don't know. Let's find out. Let me scoot this up a bit here. So let's start making some connections. So again, we know that 1 and 5 are the same, 2 and 4 are the same, 2 and 3 are the same, and 4 and 5 are the same. I'm going to start with really these two middle pieces here, because I automatically am drawn that angle 2 is at the forefront of both of those. So from those two pieces of information, I can conclude that angle 3 and angle 4 must be the same by the transitive property, or you could say substitution, but this really jumps out at me as the transitive property. But also look at the very end of our original four statements that we knew that angles 1 and 5 and 4 and 5 are the same. So again, I'm drawn to that. Both of these end in angle 5. So angle 1 is the same as angle 4, right? Again, by the transitive property of equality. Now, I'm going to go back just a hair here and mention really the one number that we were talking about originally. Remember, we had said originally angles 1, 2, and 3 were going to add up to be 180 degrees by the straight angle postulate, right? So wouldn't it be great if I could show if angles 1, 2, and 3 all were the same as each other? Wouldn't that be great? So the only thing I really need to show is that we already know that 2 and 3 are the same, but what about 1, 2, and 3? You know, if I could show that angle 1 matched up with angle 2, or if angle 1 matched up with angle 3, then I would really know that angles 1, 2, and 3 all matched up with each other. And that's really what these two pieces are going to allow me to do, right? If angles 1 and 4 are the same and 3 and 4 are the same, well then angles 1 and 3 must be the same by the transitive property. Oh, there's the bell for you guys to not be here. Awesome. Thank you, Bell. And so, notice now, if angles 1 and 3 are the same, then they deserve the same markings. And 3 had 2 markings, so 1 gets 2 markings. So now, notice in the end, we could really conclude here is that angles 1, 2, and 3 are all equal to each other. And we said that angle 1, 2, and 3 all added together must make 180 degrees by the straight angle postulate. So really what we could do is we could substitute out, what could we substitute out angle 2 for? We could substitute it out for an angle 1. What could we substitute out angle 3 for? How about an angle 1? So in the end we've got angle 1 plus angle 1 plus angle 1 equals 180 degrees. Once I simplify this, I have 3 angle 1s equal 180 degrees, and divide the 3 over, and angle 1, I actually get a number here, is 60 degrees. So in the end, all of these angles, angle 1 is 60 degrees, angle 2 is 60 degrees, angle 3 is 60 degrees. Also angle 4 and angle 5 are all 60 degree angles. So what initially looked very odd and maybe hopeless in terms of actually figuring out a number for angle 1, actually worked out pretty nicely here. All right, number 2, using the diagram, which rays are parallel? And we need to explain our reasoning, but again, no formal proof is required. We don't need to do statements and reasons here. So notice I've got some angles, but I don't really have all the angles, right? I'm noticing I don't know how big this angle is, and I don't know how big this angle is. And this, hopefully, is really going to kind of cement and solidify the straight angle postulate, because I know some people still are a little confused about where exactly does the straight angle postulate exist in any given problem. And so again, the straight angle postulate says that any number of angles that lie on a straight line and use the same vertex have to add up to be 180 degrees. So point H is a vertex. It is the elbow of 3 angles. This 61 degree angle, this 59 degree angle, and this unknown angle, EHC. But all 3 of those angles collectively that use vertex point H have to add up to be 180 degrees, again, by the straight angle postulate. So if I took 180 and I got rid of the 59 and the 61, well, really the 59 and the 61 together add up to be 120, so that leaves me with 60 degrees for this angle EHC. All right. Now, not only that, but I could also do the straight angle postulate over here with vertex point E, that these 3 angles all added up together must equal 180 degrees by, again, the straight angle postulate. So if I had 180 and I got rid of the 62 and the 58. Well, again, that's like I'm subtracting away 120 degrees. So angle FEA is also 60 degrees. So now I need to be on the lookout for maybe some angles that could be really good to work with together that might present some parallel lines. So let me clear off this little work here. And really the only things that look plausible of being parallel might be like this ray EA and maybe ray HC. Another possibility might be ray EB and ray HD. But other than that, that's really the only two cases we could explore here, right? So let's start with these first two, EA and HC. And so what's going to be our transversal is going to be this line, FG. And then again, for right now, you need to do some ignoring. Okay, you need to ignore this ray. So let's just kind of ghost it out here. Let's pretend it's not even there. And really, we could do one of two things here. We could really just use the 60-degree angle here. No, I don't want to ghost it out. We could use this 60-degree angle, and we could use this 60-degree angle. And hopefully that kind of jumps out at you as a set of corresponding angles there. But we could also, if we ignored those rays, really we could take those two angles and add them together, which we've already done to figure out what those 60s were. This is really a 120-degree angle, and that's really a 120-degree angle. And then again, those two angles should jump out at you as really being another pair of corresponding angles. And what do I notice about those sets of corresponding angles? Well, I notice that they are equal or congruent to each other. And is having equal or congruent corresponding angles enough evidence to conclude that we have parallel lines? And we do, right? So I can conclude, and if you want to call, well, really I call these rays. So ray EA will be parallel to ray HC by, and again, if we ever want to prove things are parallel, these are our converse of statements, and it's the converse of the types of angles that we saw that had a special mathematical relationship. So we've got some parallel rays, EA and HC, by the converse of the corresponding angles postulate. All right, so now let me clear off all of this just so we can go look at those other rays. Because I ghosted some of them out. We need to rehide some other ones. So let me pop in the 60 degrees that were back here and here. And again, now let's focus on EA, or not EA, EB. Let's focus on EB and HD. And again, FG, line FG is going to act as our transversal. And so now what I notice is that, hey, I've got this 61-degree angle, and it's corresponding to this 58-degree angle. Also, this is where I could ghost out this kind of ray HC and this ray EA, and then I could talk about how, no, don't do that, how this is really what, a big 122-degree angle, and this is really a big 119-degree angle. So again, notice those 119 and 122 angles, those are really also corresponding angles. But what do we notice about these corresponding angle sets? They are not equal or congruent to each other. And so we don't have to write this, but I will, just so that you see the point here, is that ray EB, and then I'm going to draw the parallel symbol and then put a slash through it, so that means is not parallel to HD, ray HD, because the corresponding angles are not congruent or equal to each other. So again, I wouldn't normally write that out, but I want you guys to understand that's why those other two rays are not parallel to each other. And so again, notice, I didn't write a formal proof for that, but I kind of went through, I did a little bit of math, I saw some angles that were special and had mathematical relationships, and then I saw other angles, right, these corresponding angles, that they have a special name, but they didn't have the same mathematical relationship. They were not equal. All right, number 3, use the diagram to answer the 3 parts. So part A, find the value of x that makes P parallel to Q. So let's focus on P and Q. All right, so notice I've got two transversal options. I've got transversal R as an option, and I have transversal S as an option. Now, which one am I supposed to use? Well, if I'm supposed to find the value of x, notice on transversal S, there's only one angle here, and it's not even an x angle, right? So this gives me a good idea. I'm probably going to be focusing on transversal R, because here's an x angle, and here's an x angle. And so I got to notice, what type of angles are those? Well, those are corresponding angles. Now, here's the big thing. I currently don't know that P is parallel to Q. So even though I see corresponding angles, I can't say that they are congruent corresponding angles because I don't know the lines are parallel. What I need to do is change my statement just a little bit there. Instead of saying, because the lines are parallel, I know corresponding angles are congruent, to saying, I need the corresponding angles to be congruent in order to make parallel lines. Okay? So what I really am concluding here is we need corresponding angles to be equal or congruent in order to make P parallel to Q. Okay, that's what I'm thinking in my mind. You don't have to write that down, but if you want to write it down, like on a quiz or a test, hey, that's awesome that you are illustrating to me that you really understand that concept. So we need 2x plus 2 to equal x plus 56. Those are the corresponding angles we need to be equal, right? So let's solve for x. So let's subtract this x over to the other side. At the same time, let's go ahead and subtract this 2 over to the 56. So cancels there, cancels there. So in the end, we've got x, 1x equals 54. So find the value of x that makes P parallel to Q. So if I plugged in 54 back into x, this would be 108 plus 2 more. This makes this a 110 degree angle. 54 plus 56 makes 110 degrees. Hey, if x equals 56, then the corresponding angles will be equal. And if the corresponding angles are equal, well, then P must be parallel to Q. All right, part B. Find the value of y that makes R parallel to S. So let me clear off my picture here, because now we need to switch some focus. All right, so we want R to be parallel to S, which means either now P or Q is going to be our transversal. Well, which one's the better transversal? Well, again, if I need to find the value of y, well, here's a y angle and here's a y angle, and both of those are on Q. There's no y angle up here on P. So that's really telling me, let's use Q as our transversal. All right, so now let me clear off my X work here. Hopefully you guys were done with that, right? You didn't need that anymore. And let me clear off some of those reasons there. So now we got to realize, well, what type of angles are Y's here? And they are same side exterior angles. And so if I recognize what type of angles they are, so we need the same side exterior angles to be what? What do we need those types of angles to be mathematically? And we don't need them to be equal, we need them to be supplementary in order to make, this time, R parallel to S. So let's do that. Let's make them supplementary so we can figure out what value of y we would need in order to make R parallel to S. So I need y plus 7 to add to the 3y minus 17 to equal 180 degrees. So then all of this is on the same side. So I can combine like terms here. Y and 3y make 4y. 7 minus 17 is going to give me minus 10 equals 180. And so I'll add that 10 over to the 180 to get 190. And then divide the 4 over. And, geez, what's that going to give me there? 4 goes into 19 4 times, which is 16 with 3 left over. And then 4 goes into 30, 7 times, leaves me with a remainder of 2 with a 0, so it's a 20. 4 goes into 20 5 times, so 47.5. And initially you might go like, ooh, 47.5, is that okay that we got a decimal there? And hey, unless I screwed up the math here, let me just kind of double check. Yeah, we're good. It's 47.5, yeah. So if I were to plug numbers back in, 47.5 plus 7 gives me, what is that, 54.5 degrees for this angle. And then 3 times 47.5, let me grab my calculator out here. Yeah, it's okay. I got to use a calculator too sometimes. So 3 times 47.5 minus 17 gives me 125.5 degrees. And will those add up to be 180 degrees? And they do. So perfect. Y must be 47.5 in order to make the same side's exterior angle supplementary in order to make R parallel to S. All right. Now part C. Can R be parallel to S and can P be parallel to Q at the same time? And you might go, yeah, why couldn't it be? You know, if X is 54 and when Y is 47.5, then P is parallel to Q and R is parallel to S. Yeah, that works. Why is this even a question, Mr. G? And so I just want to point out one other thing here. If you remember, and I'm just going to go back to our Y work problem here. Do you remember when we said we wouldn't choose transversal P because it had an X angle in it, right? Well, on our transversal Q, notice there's this X plus 56 angle, right? There's this X plus 56 angle, and we already saw for what X was, right? X was 54, and how big did we say that angle was altogether? This angle was 110 degrees, right? And this angle was 110 degrees. And that's how we ended up showing that P was going to be parallel to Q when X was 54. But I want to point out something if you haven't already seen it. Notice these two angles that are adjacent to each other, and they form a linear pair with each other. And what should linear pairs add up to be? Shouldn't they add up to be 180 degrees? And do they add up to be 180 degrees? No, they add up to be 164.5 degrees. So initially you might go, oh, I must have messed up my math somewhere because that clearly should be 180 degrees. But no, this is really the importance of this question. Can R be parallel to S and can P be parallel to Q at the same time? And the answer is going to end up here being no. No, it can't. Because the linear pair of angles, and can I name those angles? No, I can't really name them because I don't have any letters to work off here. So I'll just say because the linear pair of angles, the 110 degrees and the 54.5 degrees, are not supplementary. Now, if these two angles actually did add up to be 180, then yes, all, or not all, it's just two, but both sets of those lines would end up being parallel to each other. All right, the last one. Ooh, we saved the best for last. We got a fun proof here. All right, so A is parallel to B, given to us. A, B, so I'm just going to give those the green light go here. All right, and angle 3 is equal to angle 4. Well, if I look at 3 and 4, they don't really have a name with each other. They're not even on a common transversal, but it doesn't matter because they are given to us. So that means I automatically get to make that a solid connection. And if I want to write on here, I'll just make a little note that this solid connection was just given to us. So let me start off this proof. I'm just going to actually write this out instead of just circling it and dropping it down on a line here. Okay. Now, we need to prove that angles 1 and 2 are equal to each other, which gives us some very valuable information. That tells us that angles 1 and 2 must be our incomplete connection. Now, I would not draw the incomplete connection going this way because it's crossing over my given information. So I'm going to wrap it around the given. So which way would be ideal here? Let's go around this way. There we go. So now I got to figure out how my given information and this incomplete connection that angles 1 and 2 are equal are somehow going to make a complete circuit of angles. So I need to try to find some angles. And again, we were told that A and B were parallel to each other. No, I don't want to take a picture of that. That was the wrong button. So maybe I look over here at angles 1 and 3 specifically. Do 1 and 3 have a special name? And they don't. Well, shoot. But could I draw in an angle 5 that would connect to angle 1 and would connect to angle 3? And yeah, I certainly could. And there's lots of different places you could drop that in. So for instance, I could put angle 5 right here. It would be corresponding to 3. And it would be, what, straight angle postulate, a linear pair with angle 1. Or I could put it right here. And then I'd have same side interior angles and vertical angles. Oh my gosh, stop interrupting my video. Oh, jeez. Could I put angle 5 right here? Yeah, alternate interior, straight angle postulate. So literally I could put angle 5 here, here, or here. And I get connections with 1 and 3. Does it matter where I put it in the end? And honestly, it doesn't. So I'm going to put it in that last spot. I'm going to put it right there, okay? So I know 3 and 5 will have a solid connection because they are alternate interior angles in the presence of parallel lines. So I can talk mathematically that they're going to be equal. I can make a solid connection between 1 and 5 because of the straight angle postulate. All right, so I've connected 1 to 5, 5 to 3. 3's connected automatically by 4. Now it would be great if I could connect 4 down to 2. But notice 4 and 2 don't have a special name. So I need to find maybe an angle 6 that could connect to 4 and connect to 2 at the same time. That would be the most efficient way. So where can we put angle 6 at? Where can I don't know. Let's maybe try putting it down here. Could we put it up here somewhere by angle 4? And we absolutely could. But we're a little crowded up here, so I'm thinking maybe somewhere down here. Could I put angle 6 here? And notice 4 and 6 are alternate interior, and 6 and 2 are straight angle postulate. So it's really kind of like those same angles that we had over there with 1, 5, and 3. So sure, why not? Let's do the same thing again. So 4 and 6, again, alternate interior, and they're based on parallel lines A and B, so solid connection, we'll know they're equal. And then 2 and 6, once again, straight angle postulate. All right, so now if we look here, I've connected 1 to 5, 5 to 3, 3 to 4, 4 to 6, 6 to 2, which will incompletely get me all the way back around to angle 1. There is my game plan. Now I just need to write it all out. Now, where do I recommend starting after the given? Well, I would either start at angle 1 and kind of work my way along this fun game board to get to angle 2, or start at angle 2 and work my way around through all these solid connections until I end up at angle 1. Which way should I go? It doesn't matter. But I'm going to start with angle 1 just because, hey, it's angle 1, why not? So now I need to talk about what was that connection between angles 1 and 5. And if I write out those connections in my game plan, it'll help me write the proof maybe a little more quickly. So we knew angles 1 and 5 added up to be 180 by the straight angle postulate. All right. So now notice I do have two pieces of mathematical information here, but in my game plan, those two things are not connected together, right? They're kind of disconnected between angles 3 and 5 here. So I'm not going to do any substitution yet. So now I just keep going along in my game plan. I talked about 1 and 5. Now I'm going to talk about 5 with 3. So what was so special about 5 and 3? They were alternate interior angles. And with my parallel lines, they must be equal. So angle 3 is equal to angle 5 by the alternate interior angles theorem. Now, here's where I've got those two back-to-back pieces of solid connections, and I've written about both of them. And so here's where, just highlight these pieces in my proof, these are those two pieces that are back-to-back solid connections. Now it's time, ideally, this is where I would do it, let's do some substitution. Let's take these two pieces, and who's the middleman between 1, 5, and 3? The middleman is angle 5. So that means angle 5 is going to make its departure through some substitution, or maybe transitive, but at least substitution. So notice, angles 1 and 5 add up to be 180, and angle 3 is equal to angle 5. So there's again the common connector, angle 5. So we're going to state that angle 1 plus We're going to swap out angle 5 with its substitute value, angle 3, equals 180. And so there's true substitution. That is not the transitive property. All right. So now I've connected 1 to 3. And so now what I would typically do is talk about the next solid thing in the proof, which is 3 to 4. But I've already talked about it. It's back up in my given. So we are already ready, boy, say that 5 times fast, for the next round of substitution. So now I'm going to take this piece of information that I just concluded, and now I get to combine it with this piece up here in my given. So based on those two things, if angle 1 and 3 add up to be 180, and angle 3 is equal to angle 4, so keep in mind, I've got this 1-3 connection, and now I've got this 3-4 connection. Who's the middleman? Angle 3. Angle 3 is going to bow out so that we can connect 1 to 4. So angle 1 still going to stay in place, but we're going to swap out angle 3 and swap it out with an angle 4 based on that given. All right, so there's another round of substitution. All right, next up, now we got to go talk about 4 and 6. It's the next thing in our game plan here. So 4 and 6 were alternate interior. They're equal to each other. Why? The alternate interior angles theorem. And so now we got to pause. We're going to do another round of substituting. So if 1 and 4 add up to be 180, and 4 is equal to 6, who is our middleman this time? Angle 4 is the middleman, or middle woman. So then angle 1 plus swap out angle 4 with angle 6 equal 180 degrees. True substitution. All right, so now let's go back up here. So we've connected 1 all the way at this point to angle 6. We got one more connection to get through here. So now let's talk about what's so special about angles 6 and 2. And 6 and 2 we said was the straight angle postulate. So angle 6 plus angle 2 equal 180 degrees by the straight angle postulate. All right, now, last time of doing a round of substitution. We're going to take that 1 and 6 relationship that added up to be 180, and now here's this 6 and 2 relationship that add up to be 180. And man, I'm running out of space here, so I need to scoot all this up just a bit. Now, in this time, we're not easily just going to like magically get that angle 1 equals angle 2. That would be doing too many steps at once here. But what I do notice is that 1 and 6 and 6 and 2 both are equal to 180. 180 is my common connector to bring these two things together. So what I can conclude is that angles 1 and 6 are the same as angles 6 and 2, right? Because both of those sets of angles add up to equal 180 degrees. Now, you can either call that substitution, which would be your safe bet, or really this time, that could be considered the transitive property. So it's up to you which way you want to go. Now, remember, I was trying to prove that 1 and 2 were equal, but I got angle 6 in the way. And so what could I do algebraically to get rid of that angle 6 on both sides? And we could subtract it on both sides. So in the end, if I subtract away angle 6 on both sides of my equation, then I would finally end up with that angle 1 is equal to angle 2. And there would be the end of my proof. So you might look at that and go, OMG, that was a long proof. And no, I don't want to take a picture of it. It was a nice proof. I don't want a picture of it, though. Thanks, Mr. G. Yeah, that's a really long proof. Why did I give you such a really long proof? Because this is a challenge day, and I wanted to challenge you all. Now, will you have any kind of proof on the quiz or the test that is as long as this? And the good news is, probably not. More than likely not. Will you have a proof that might be a little bit shorter than this? There's a really good chance that that's going to happen. But anything this long? Probably not. But you know what? If you could do this proof on your own, and it may have made just maybe some little mistakes here and there, I think that's fantastic. You know, as long as you can knock out most of this and you're mostly right, that's great, because these are really tough problems. All right, so hopefully you got most, if not all of those right, and now we can get ready for the next quiz.